And today is remote lectures. Now they will be repeating some of the stuff which we still talked before, but going to some detail. But I should say from the beginning that some projects that faculty do, where they're very deeply involved, like very scientific, very like physical, all kind of things. Usually those are the ones where we get the grants, funding for those projects. And there are projects where we actually supervise student teams. So this project is actually where we have generations of student teams. So I don't know much details on every single thing. I'm just going to go through the background of this information because, as my understanding is from Dr. Guillermo, that's one of those projects where we can have some good collaboration. And again, it's interesting because there was like layers and layers. There were some master students who defended, but master students were supervising undergraduate teams, and we were getting return on grants for this, etc. So there was a lot of action for these projects, but they were like doing it yourself thing. Okay, so yesterday I talked about that we have the albatross bird as the natural example of how we can fly without much consuming energy from food or anything else because they do the maneuver where they can extract energy from the wind, from shear in the wind. And that's the case where we're trying to replicate. But for this, you need to like teach the aircraft how to fly properly and learn things. And that's where this artificial intelligence, in terms of machine learning, in terms of reinforcement learning comes together. Now, this is a citation from Lord Rayleigh, I mentioned yesterday, from 1893, where he was mentioning the only way this birds can actually fly is probably in the course. They can have the courses if they're not hanging. If they're not flipping the wings, it's going to be the course is not horizontal, so they go down. The wind is not horizontal. Other wind is not uniform, and that's actually was the case. Of course, it's not uniform, but he was actually making us clear. And then there were papers later, much later, like 100 years, 80 years later. In the 64, Clarence Cohn, in his paper here, came up with a more strict analysis of this whole process. And he was talking about what happens with bird when it flies, talking about the camber, which produces a dihedral, variable dihedral thing, which has to be there. And at the same time, he was talking about the trajectory. Trajectory, how they fly to wind, and with the wind, so that's what we call dynamic soaring flight, and that was actually when they removed science of this whole flight started to develop. So this is the actual maneuver, which we do this sort of wind shear. You can see here, that's essential for extracting the energy. Then you basically go through the 4 stages, as I mentioned before, where you have to basically climb and go down, climb and go down with some turns, and that will allow you to actually take the energy out of this flow and basically fly without battery. That's the idea. So basically, this was the 4 particular stages I mentioned here: low turn, through a line, how you turn, they will descend, all those things come together. And the project goal was, in this case, kind of trying to teach the aircraft to do these kind of things. So that would be on the pilot, which will automatically like adjust the flight, responding to the wind conditions and everything. And that was the idea. But on top of that, there was an idea, which was like, we were very, I guess, enthusiastic about this project. And saying I wanted to have something new, and I was actually doing the variable span, variable sweep, variable dihedral for the flights. And the students took this task, but as I mentioned, everything here was done by master students, and there was no PhD involved, which would be nice to have. And for master student, they had 1 year, so they started. Okay, I have to graduate already. Sorry, I cannot do this. So that 30 bits of here and here and here and so. So that was the history of this project. And then, of course, they also provide the student, like undergraduate teams. Well, the undergraduate teams actually, it's another thing. Have the same experience probably because they really have to find time because they take like 6 courses each semester, 18 hours sometimes. You barely find any time for any kind of research. And they meet, some people come, some people don't, so that's a mess. So yeah, I mean that's that's not how business works, right? But that's what it is. Anyway, so the first generation of student and student teams, that was Wes and Joseph. My former intern actually came from India, and then he was replied for become a bachelor degree and work with me. Well, a very bright student. In fact, right now, he was at Boeing, became like a really famous guy there because he proposed some ideas how to use AI to measure velocity of the aircraft, not by pitot tube, but by sound. You can actually hear the sound and you can determine when you fly, you can determine what speed you are. In fact, you can do it in your car. And that's how he actually started. He actually was putting the microphone next to the car when he was driving. And depending on the sound that you have for the flow around, he can determine what speed it is. So he proposed this idea to Boeing. They were just wow. So he got like some award or something. He was almost like nominated for like the best some engineer for AAA because that is a bright idea. And then now he left Boeing because Boeing is a huge, very I would say unaccommodating company. So he's now at some startup. I think it's Archer. In fact, now I think he's in Florida now. Ben. He said that he would invite me to go lecture there too. But Archer is a competitive job, and we work with jobs. That's a bit of a tricky thing. I cannot be everywhere. They are very curious about this stuff. Anyway, so but this is an idea you can actually look at it. And then how it works for this his idea is that this is all AI. So you record every time you train the system, and then you can put it on Boeing, and it will figure out depending on the sound, it will tell you what the speed is. You can do it yourself, by the way. So that's not an interesting idea. So if you, for some reason, cannot determine your velocity, you can actually get it just by the sound. Like open the window and get it. All right. So that was his original task to develop the maneuver using MATLAB. So he didn't progress much to reinforcement learning. He only got to the point when he established his whole infrastructure, all his modules put together, and he was able to relate with them. So he was actually sort of manually piloting the dynamic soaring thing with all the components put together already. So that's what he did. And in the end, you'll see these results here. And but yeah, he did a lot of things on the way, and that was the way he started, which was continued later on because you do need to involve some variable fidelity tools for analysis, like aerodynamic analysis, because you need to understand all those coefficients, like all aerodynamic coefficients. And for that, you need to run CFD, and that would be ANSYS, and he was also running Surface, which is Telenet, which actually was developed by Goodness, which I mentioned before. So anyway, so this is his conditions for the grid, which he was doing. This is the aircraft, how it looks like. That's the one which he was developing for dynamic soaring. And then he was actually putting this in a surface model, this is the panels. All the conditions there. So there's a high and low fidelity models, and he was comparing. And again, the low fidelity works fine at low angle of attack. Go to the high angle of attack, low models don't work. You have to go to RANS, something like that. Have the predictions look with me and coefficient. This actually shows. So he established this whole thing. And later, like Jacob Adams, my other students, continuing on the same line, but here it was down. So at this stage, you can see all these coefficients, so like CL versus alpha, like you will CM 777. But this is an example. He also experimented with different turbulence models. That's important because you need to understand which you can trust. So there's some experimental result, which was obtained using some studies which was published in NASA. Experimental 2D data, experimental 3D data, and then you have different like Almaras, DES, so on. So all this came, so all that stuff he was putting together, and he was comparing which model was the best, and that was the one which he was using later for the system. Really big performance. of this aircraft during these maneuvers, right? So that was the idea. Eventually, out of my morphing request, that some morphing thing, he only did the 8 feet and 10 feet or 12 feet. We'll see that, just to see the differences. So that's the different stages he was looking at. Joints, see the joint angles here. About the wing, so you have the stage 1, stage 2, stage 4 should be somewhere 3. So that basically he was running simulations for that in the stages. And then he was also looking again the difference in wingspan, 8 to 12 feet, and see which stage of this flight you get advantages. So the idea was to be it's morphing, so there'll be some spare, then will be withdrawal of this. So you fly like not just all the time, but then of course you can fly more than like this too. But that's he didn't do. So only did the extended span. That was his process. So you see there's benefits of different spans at different stages of the flight. So if you have and that's what the experts do, but they do it differently. They just so they do kind of contract the wings in some particular cases when they maneuver. So they do employ this thing. So it's again everything comes from nature. So that's another thing, which is we can implement. So this examples of 8, which is 12 feet, low separation on stage 2, for instance, one of the stages of flight. He was experimenting which one. So you see the stage wingspan 12, for instance, shows much better on scale compared to wingspan 8 because this one shows a lot of separation. So that's the thing. Yeah. Because stages of flight. And from there, he started to develop this whole environment. So this environment involves a lot of elements which come together in a flight simulator. You probably use a lot, like MATLAB simulator. So that's actually part of the MATLAB simulator stuff, putting all together all the spots with the autopilot controls. You can see here with the weight control, you need to go the position, like where you fly, and then with that condition, you actually have to try to reach this condition. So there's waypoint directions, which are embedded into this system. And then you have the, you calculate the distance for the next waypoint, and that's how you side location, ground location, range calculator, all the elements come together inside this system. And then you will see employing the weak model, which is synthesized, but that's coming from the standard model for the atmosphere, which I think FAA actually. So excuse FAA standard model for the wind shear. They had and that's what we use. This is actually one. We see there. So mean good velocity, some altitudes and so on and so on. So basically you use this kind of profile which you can put together. And then the pilot controls in and out of control loops involved, like deviations in errors and corrections. Then we go to the flight gear implementation stage. See a lot of details all inside. And that's where he was working a lot with the teams from the grad school to go all together. As I mentioned before, there's actually advantages. We have the advantage that we have a lot of design courses. So students are really, really good at putting everything together. So they like simulating is basically their second nature. So they all know. You probably use it as well, but they have like a lot of stuff for which I don't know much fun as well. But anyways, so then we find out that more like it was doing some modifications. See that kind of wing becomes more of a bird-like, like looking not just straight. But there's some variable that we do. And then he was flying this thing and seeing how this thing evolved with the different speed variance for the 30 feet different wind speeds and so far it behaves. So it's actually manual pilot involved. And eventually he was looking at the total energy, how much he consumed, how much he can sustain, pretty much everything that Jacob Plater did in the automated system. Yeah, reinforcement. But he was basically doing this all by himself with the manual pilot. First we started with Soaring, so it was implemented all this thing. See all these things here. It's a human piloted dynamic soaring. That's the point. So the legacy of all this work went later to Jack. That's my second student. With his team. That's how you pilot. You can do it. That's the things. It was a lot of fun for me. Human pilot. And that came Jacob. So after actually it was some intersection like a few weeks because I needed to provide continuity. So all the legs of the work she gave to Jacob, who was head of the other team of undergraduate students. And with that team, we did get the work, as I mentioned, I call it my project, my work from the university to develop and build and fly. This is actually the Fox aerobatic glider, which is still sitting in my storage, as I mentioned, waiting for the break guy. But that's actually what they were trying to equip and fly with the automatic pilot system. So the idea was actually now to use the reinforcement learning to provide the flight path, which was manually piloted more as before, for rotordynamics for given reach shear conditions. So there will be some inputs coming from the sphere condition, but in the wind directions and everything else, and then you would be flying automatically using this system, which is network based. What I mentioned that it will be like offline training, and then there will be an online training as well to make it more precise, because we cannot teach everything offline. So several stages, and I think the only thing which was implemented is offline, so we're able to do it again on the computer. So if you start flying this thing, while we can continue this project, they will have to implement another stage of the redesign of the system. Project, of course, like it's a nice PhD project. This PhD project actually is taken from a number of small projects sometimes. And for instance, we have the students who actually supervise masters, and whatever master's project is going on, is part of this incorporated on the big PhD. So that's how the system works. Anyways, so this is the idea, was to develop this reinforcement learning, eventually deployed on a Raspberry Pi. That's how part of the system inside the box. And with further research to see how the bridge is gap between simulation and reality. And that's what requires some online training as well. I assume. I mean, I don't. That's something which kind of forward to do this. And so this part of it pretty much I talked about yesterday. So this is part which relates to the interaction between like an actor and the critic. So we have some mentions we do this policy implementation, and the domestic, stochastic, romantic with the neural network. Eventually, they chose paths of deep domestic policy. Gradient DPG, which was used. Environment is the world outside, patient action, patient controls, reward. That's what the critic tells the dash if it's good or bad. There should be some judgment there. Conservation defines ground states, it's good, etc. So all these components put together needed to be employed as part of this big simulation environment together with what has been done before. So the prediction part didn't change that much. We still use ANSYS here, fluent, and then still surface a little small and tag. But this part was added to this now. And you can see here, this is active network, the neural layers, in layers. And this is the active network and gradient network with lots of components, which are put together, you get the simulated environment. And basically what they do is do this implementation of the controlling the actions, right? And giving the reward for the good actions, or reward for bad actions. So DTPG, some details. So this is here. I should say that there was some experiments done because it's different, I suppose. General like policy gradient theory of some history was developed in the 1999. So it's very recent. It's only like 20 years when they was doing this kind of things. Like the theory was developed by Sutton, for instance. Uses so-called greedy policies to select actions with the highest estimated value. Yeah, that's this capitalist view, right? Whatever is good to that was bad. Explicitly represented by Hopkins approximator and so on. So and then there were like elaborations on this specific theory, which started developed specifically this hypothesis gradient algorithm was developed by Silver in 2014, very recent. Big well, it's only like 10, not even 10 years. Well, yes, 10 years, 12 years. That with this algorithms actually have been development. And less international effort compared to stochastic policy, degrades only over state space rather than legend state. And then I don't even know when this guy developed G. Let's hold it demolished. So that's latest, and that's what we use. It's model 3 online of policy at the critic reinforcement learning algorithm. Uses deep neural network function approximations, a continuous action observation states, inspired by deep Q. So, anyways, this is the one which was very selected. I think based on some experiments, all this are implemented in the MATLAB simulate. You can play with them and see which one will give you better output. But that's the one which, after several iterations of trial and error, Jacob decided that that's would be the best. All right, and now it goes into this PPG algorithm implementation, which basically was implementation on episode loops, initialization. Sorry. So there's a critical network, the actor with its own parametric assignments, the right amount of space, so on. So like mathematical formalism, but this basically shows how it's done in terms of specific parameters, which are included in the flight explanation. And the episode loop, you receive the initial observation state, and then you loop in time. It's all things which the DTPG does as part of this looping in time. Select action and repeat actions, so experience, sample random batch of experiences, set the value function, update critic by minimizing the loss, update the active policy. In a way, again, this is what how learning is done, and how it's actually rewarded. But it's actually all split into a number of steps, very clear steps. So this is actually how it's all done. So this is this system of active critic implementation for each particular episode group. Let me do this, and there's a training process. It's part of this. That's how it's done. So this is has been a much implemented in this particular papers. It was a conference on machine learning. 2016. So that was actually 2016. 10 years. Celebrating 10 years of this algorithm. How it's actually done. Very recent. So that was all implemented in the autopilot system. The objective was to develop this, and then it should be updated again with the dynamic predictions. So for this particular glider, so we have a particular glider. So before it was whatever, and now we have a specific thing for which we're designing the autopilot system, so we can actually fly it well. And so all the coefficients which we've calculated were based on specific parameters of this particular glider, including the mass inertia and everything else, right? So then you have the 2D CP analysis done. So this one has a Clark wire foil. Basically, you can run it because there's experimental data available to compare predictions for the different profiles. So both 2D analysis was done and then 3D analysis to obtain all these coefficients. Whereas flow conditions, again, the angle of attack was changing between minus 40 to 40 degrees during this maneuver. Side sleep minus 40 to 40, roll minus 90 to 90. So it's a because of the state, right? So you have to remember this huge difference in the angles. And so then you have this Rotordynamics method was chosen for fast calculations for the medium range of angles because this is a panel method. So this panel method, with this guy because it's expensive to run for every possible case. So that was combination of things. Turbulence model was developed as usual. Selected as usual. And then RANS, that's what you always run, random establishment in Stokes. Point-wise, the regeneration, angle protect, simulations to turbulence models, which were also selected. And there's a lot of analysis here to see which one is the best predicts the experiment with the plan and UI UCM. That's one of those. Yeah, somewhere was wrong, some window. And you can see that CL pretty much is well predicted by all models. CD is not as much. K epsilon is actually very bad compared to others. And then this guy, CM, actually pretty much different from experiment, but they're all different. So CM was a bit tricky. CD, all models are overestimated to try to compare the experiment, and same for the mesh models. Yeah. So, yeah, they works best. But then, of course, it just gives you some rough estimate. You should need to put in the model and see what happens in reality, right? So that requires some iterations anyways. So 3D CFD analysis, that was actually 2D. The DCFD analysis was done on the actual aircraft, not just the particular profile. As I mentioned, RANS was run for radius 300,000. So again, that's specific to the airport journey for this particular thing. So parameters I mentioned here, atmospheric and flow property, which was included in these simulations. Point-wise was used, compensation was done. That's how it looks like. So you have a small box where you have this very fine mesh, which is surrounding the aircraft itself, and then you have far field mesh, which you have propagated in distance away, with some flow conditions, and so on. So you see this clustering of grease in the aircraft. And all this parameters for this connection is right there. And these are results for the angle text sweep. Small change in light of coefficients and so on. You can see that, that's what you got. That's this point, we don't know. We hope that 2D predictions, which will validate the experiment, would pretty much validate these results as well. But we don't know. There's no comparison with experiment yet. So it will be like during the test, we will know if it actually works or not. We'll fly it finally. So this is a stage where 2D does the validation and 3D is basically your hope it's going to be good enough. So all the pair sweeps, all sweeps, so all that stuff. And surface was also used because surface can do the entire course aircraft. But of course, it doesn't have much thickness like solar panels. And again, you can maybe validate this to see how good it is compared to the CD developments. Yeah, that's what we start. So actually, this is a comparison between VLM, surface data, and CFD. And you can see, as expected, at the small angle up to 10 degrees, your CFD and your panel methods predict more or less accurately, the same. For all these conditions, CFD, CL, CM more or less, CM is less. But then if you go further, if you go to the stall region, there's a huge deviation. So that's where the panel methods are typically failing because they of course potentially inefficient, so they don't predict any kind of viscous effects, roots, breaking, all those things. So this is actually was used later to predict the derivatives because we need the dynamic derivatives. That's the thing. So that becomes a bit of an issue because, not an issue, but you need to realize that whatever inaccuracy you have there, it will be carried with a much more severance in the coefficients and the derivative. So, but anyways, that's what we got. So right now, this is the data which we converted to an autopilot. How it's going to work, we don't know because we didn't fly it. So there's a hope, but there wasn't to tell. So whenever we're going to fly, finally, it's still we'll see. Dynamic stability analysis was done on longitudinal lateral dynamic stability technology. We built including purposes. Actually, that would be the for the limited range of the angles which surface is going to form. Some results are shown here. Roll conversion scalar depth, slightly depth, so that shows the depth. So all this stuff is actually what's usually people need to predict for the control, dynamic control, dynamic stability control, take a second. And finally, dynamic model, all the stuff is predicted using this predicted static coefficients and líderes. So that's what also applied to the other pilots. Actually, all the stages are important. So flight model integration is a MATLAB simulation combined with 6 degree of freedom of operations of motion, develop thrust model as function of SV, propeller rate, physical dimensions, and straight angle rates, and deflection limits of control surfaces. So see all the steps. Used to the methodology dance. She made familiar. So eventually you build the same kind of model which was done previously by Jacob, but in the more sophisticated way because now it operates built-in reinforcement gunning tools as well, training model, training model. But that's what it is. So this is very old implemented for specific aircraft now. Allowed for development of dynamics on maneuvers for the Fox. And the components include all this hookup tables, where dynamics, total force moment calculations, wind shear moment, propellant thrust, model joystick, built-in visualization, and reinforcement learning training. So all these components are part of this big MATLAB simulating environments. Can be tested, see how it works, and hopefully deploy it almost autopilot. The linear equations, which I already as part of this, force equations for the aircraft for the velocity components, including the wind shear equations, which are here, coming from something which is, of course, in nature it may be different, so that may be updated. One of those things which may be updated online for the more accurate predictions. So, kinematic equations for the angles, angle derivatives, rates, equations, moment equations, we have navigation equations, eventually all these things put together. And the application was done with the, looking at the single agent, I've got it energy signal agent algorithm, where agent controls UV and optimizes DS maneuver. Engine is free to explore environment and determine most optimal DS maneuver. Goal is not to crash, maintain total energy over the time. So that's it. Same energy. Now, there's a double agent methodology as well for agent A for path optimizing agent, optimizes path for soaring unit rather than previous UV states. For agent B, path following agent follows path with this little thrust possible. Double agent safer to deploy and really efficient paths very tempting. So the options how you actually guide your route for the single agent or double agent methodology. That's stuff. Path following agent, which is basically this agent B. What we do the waypoint algorithm, so basically calculates the error between the path. The training as the inputs, like look at point, like review position, review altitude, flight paths, and so on, and output position error, angle error, flight path error. That's how you actually determine to minimize the error to stay in course. The waypoint Yeah. So there's several generations of these attempts for different configuration, like pitch and roll, observation, rewards, function, angular error, research function, so on. But we're trying to get at least on the same trajectory for the circle behavior, like so, and that was implemented through several stages. So, for instance, in the generation one results, he almost got it, but still the target wasn't here, but he was getting this blue line instead using this algorithm wrongly. So we're still pretty much in the first times here. It's altitude. So the altitude varies, so it's not going to straight what we want. It's not like stable, so it goes all over the place. But that was the first generation of this attempt to get it done. The second configuration, neural network size was significantly reduced time to the optimal policy. Mini batch of randomly sample experience significantly increased. So there's a lot of tweaking around for this reinforcement learning algorithm to try to get it performing as good as possible to follow the trajectory that you want to get. So you get this mini batch of randomly sample experience significantly increase. You have the stability. So actions similar generation one. So that's additional observation. Edit lateral flight paths to enforce flight detection. Rewards edits flight paths. So there was some manipulations in the rewards. But eventually, again, you want to follow the slide and you like stick to it now very well. So that was actually much more success. So with all this tweaking and algorithm, he was able to get it much closer. And look at that for the altitude also, you kind of fall much better now. It's not all over the place. So that was second configuration of this configuration. Configuration 3 of the path following agent with some improvements for the roll and pitch PID controller tuned, duration flight outputs of the elevator and so on. See, there was a lot of experimentation. It's a fun project. You can do a lot of things. And then observations and rewards. And just getting better and better. The final configuration 4 was with the specific reward functions and actions, directions. That was like this. So actually, this is the case. You could follow up, which could change, not just the same. It's actually changing. So the fall is very accurate now. With this latest generation of this attempts to retune the algorithm. See, that's Netherlands. So that was the final trade agent applied to different waypoint paths and determine altitude. So results. There was still some problems at that point. Then he looked at that guided energy seeking agent configuration. Okay, so he switched to another guided energy seeking to see if that will give you a better way to follow the right path. And some details about this here. With all this again, actions, activations, rewards, time. Okay, and that was the winner in the end for his forward attempt. And for the trial and error attempts, he was finally able to get something which would follow not just the altitude, but it was following the path, and at least retaining the energy rate. So it was the energy was still losing energy, but the energy rate was pretty much constant. That's the red line. So this one was still going down, and this still going down. So altitude was still losing for this maneuver, but there was a hole, and that's when there was a. Then that's when he left. That was the end of his thesis. It didn't really quite succeed, but he was close when he attempts trial errors. And then there was a final guy came and he didn't do thesis on this, just do it like because we got the Ignite award, so he was actually getting some high. But he was he was still a bachelor degree. It's finished. He moved to San Diego. I can just write down because he was there on some sort of internship for the whole year. I don't know. Now he's going back to the PhD status there. Very smart guy, really. And eventually, as I mentioned, he was playing around with reward functions. So his focus was to see if the reward functions will make this thing work, and finally it worked. So that's where he had succeeded, maintaining the same energy more or less, the same altitude, some variations, of course, but still. So that's where we stand. So whoever was brave to pick it up from now, that's the stage where we're at, right? So, and again, the glide is waiting. We gotta put it all there. This is sitting right there in the storage, waiting for everything. So that's the overall conclusions. Variable fidelity hybrid aerodynamic model was generated for this box aerodynamic glider. 60 freedom of simulation environment was developed. And the reinforcement learning performed to assess different methods for dynamic soaring, so glide, etc. The future work is basically to finish the job. Flight. Yes, that's the idea. That's I hope that will be the area of liberation. Somebody wants to go. But, a lot of things was done. A lot of stuff is done. I have a lot of materials, papers, and the actual model is there, so you can play with it. And we got the money to assemble the entire autopilot system. So different components for the computer was the biggest thing, and everything else was there. So it's an old work with flight, which is quite. Oh, the latest guy who actually did the work was my Stanley PhD student, but he is focusing on NASA project, and now he got this smart DoD award. It's a special fellowship for really smart guys in US. So he is now full support. He doesn't require any kind of grants or anything. He has full support for everything. And actually, we'll have next week communication with his DoD supervisor and Navy. And but he was working on this in a bit. So he worked at his spare time because he works in series of things at the same time. I always have to hold it because he jumps on this. He actually worked on the energy extraction as well. Actually, he was the one who developed the reduced model for this one. And now, he's all over the place. So, but you need to keep him focused. That takes time because he's usually everywhere. I want to do this. He never sleeps. He always whenever I see him, he's sleeping. He get enough sleep. So he works a lot. Very smart guy. But he could only do so. If anyone is going to do this, he can actually share some knowledge, some experience. But also green guy, also he's ready to do this as well. Although he's now in San Diego, but can easily communicate because he was the latest guy who has the whole package. With him, who was actually working on a computer to tweak this algorithms. So it's well. So when several people, it's not really completely gone, which happens many times. That's the worst. People are completely gone. That's it. Just leave this. It's very large. He is right here, standing. See, standing. It's the guy on top, right. Anyways, any questions? Yeah.
Sure. Thank you for
Beware, I don't know much. I can tell you from the beginning. If you ask me about some specific details, I could say talk to Stan.
my question is, do you think that control using neural network for fusing control can largely replace traditional PAD control, or will it be used more as complement?
Would the reinforcement learning be complementary to the other things? In what situations? Like for instance, right now, what Glasson was doing with the speed determination is complementary. So you already have the aircraft with PTO2, but if something happens and nobody knows what to do, because in many cases that happens, the aircraft lost ability to gauge its velocity or any kind of things, and that was disaster. Like the was destroyed. But this one thing is actually working on the sides, reinforcement learning based a system to determine the speed by sound. So that's complementary in this case. In this particular case, I think it's all reinforcement learning in this case, because that's how you do the maneuver. I mean, you still keep, I mean, it's embedded in autopilot. Here's how you do this maneuver. Right? It's like you already, like, do you consider yourself as an example of reinforcement learning system? You walk it, right? So you went through this process already, it's embedded in you. So you know how to walk. Or ride the bicycle, right? You like dropped several times. You got a word when you were able to finally ride for 10 meters. So that's it. I mean, that's reinforcement learning. It's all there. So it's already embedded.
And from what I see, most of the simulations and the work has been done at low altitude, right?
What?
And most of the work has been done at low altitudes, right? No.
Not necessarily. Well, okay. You need to find out where the shear is, right? And basically figure out where the wind speed will allow you to implement this maneuver. So that will be part of the guiding your judgment where you have to fly. So the albatross cannot fly like in space. There's nothing there for it to implement it. So you have to be like, I guess the one of the things which of course needs to be embedded some sort of weather input in terms of conditions, where you fly, etc. We actually have this with another project. Snorri, when he was doing his PhD, and I was his supervisor, what was exactly the case? He was trying to figure out again another kind of design, which would be using thermals. Like, because you know the thermals, that's what the paragliders use a lot, right? So you can jump and then you just go forever on this paragliding system. So that's another example. So you always know where you are.
So this technology, I mean, is being developed using the windshield, but isn't actually applicable to HAPS. So high altitude, high
No.
altitude propulsion.
I don't think
Because
I don't-
that's another phenomenon.
it's a different story. How to behave there, but then we just need to watch albatross, where they are, how they fly, what altitude. So basically, that's we're pretty much trying to mimic their flight. Yeah. It's all nature inspired thing. So that's what it is. Dynamic flight. Any other questions? Yeah.
You built the model airplane?
Not me, but somebody built. Yeah.
They have
No, the full model was actually purchased. The aircraft was purchased. It's actually available. You can get it for, it's actually $200. Literally. Or even less. I mean, probably it's even less now. Because it's a simple like RC model. And then you basically, they refurbish to implement all these elements inside. So they put out a lot of things which they don't necessarily put things which they want to. So it's like something which you can order. Chinese against, right? Not expensive at all. But the parts like computer and everything else was expensive. So we got to work like several $1,000. Mostly it's about the computer components and everything else.
Is that model like free to get for us? Like you could you share it with us?
Well, I mean, it's possible.
Depends on the on the type of commitment that you
Yeah,
want
yeah,
to-
yeah. Well, that's something we can discuss.
If we
Yeah.
had like
Because right now it's just basically sitting in my storage.
but
Then you'll need to figure out.
We will talk.
Then we will
I
talk
have
about that,
already said Professor Golubev that we are willing to do it.
Yeah, that would definitely some kind of collaboration, possibility for collaboration on this project for sure. Yes, of course.
experimentally. What do you think about the warranty of the full velocity to prove these airplanes? The warranty, for example, 15 meters per second. How do you do this analysis?
So 50 meters per second, for what?
So if you have an airplane designed to fly, for example, 15 meters per second, how do you guarantee this velocity, this full velocity?
This is not the kind of thing which you actually prescribe in this case. I think you're told determine what's available for the wind speed, etc., etc. Like you will not tell the albatross you have to fly 20 meters per second today. I'm sorry. I don't know. You'll just do whatever you can, right? It's the same thing. So this is the kind of UAV which is not given the task, get there in 1 hour. It's not the kind of thing. You get there eventually, but it will take time. And how much time, you not necessarily know a priori. So you just go through maneuver. The best thing you can deliver, but it takes time, but it doesn't waste energy. Like you don't give him a battery or something, not energy. Or it can be like doing very far without much energy, like external. It's no battery. Battery is there, but it's very small, maybe something.
A quick question. About you mentioned the model is actually spiral mode unstable. I was wondering if, from an energetic point of view, does that affect like having to constantly give inputs to restore that a moment and keep the plane stable? Like,
Perfect question for the guys. I can imagine there will be obviously some expenditure on the energy side, right? So there will be better, of course. You need to do some kind of, feedbacks on this kind of thing. But I'm not sure how much it's needed, et cetera, et cetera. That would be the question to the guys.
There's something that I would like to add. Here in the areas, we have a lot of undergrads and also.
Yeah, that's the perfect project for that.
Yeah,
Yes,
exactly.
Yes.
That's what I was thinking
Yes.
about. So, for some of you who want to actually work on this, you have to take. I would recommend, you don't have to, but I would recommend to take the aerodynamics, the incompressible flow aerodynamics class. Also to take the flight dynamics.
Dynamics and control, of course.
Yeah. And please take note of this. We are expecting Professor Ever Moncayo to be with us in
He
July.
was the one teaching controls, yes. So
So
dynamic and controls.
He's
yeah.
the expert about it.
Exactly.
So, of course, talking to each other first, we can make this happen. I would say to start giving you data useful.
He's coming in June, right?
Yeah, I think it is. Yeah,
July?
in July. I think in July.
Okay. Anyways, yeah.
So, if you want to, you can already sign up for this class. It's going to be quite interesting, and he's also will be coming in the next year and also the year after that for a Fulbright program.
Yes, yes, he'll be here the whole year, all on and off. Like me, I was coming to Kazakhstan, but I was not staying the whole time, but I was coming periodically.
And please take note of this. There have been at least 3 projects that Professor Golubev have showed us until this point, and there will be more ready to be taken. So it depends on us. So
This actually would be the best one, the grad side, with some supervision for graduate students. Yeah,
we can make it.
that'd be great.
So I will schedule research seedbed, the ones that I was talking about like before, and within that research seedbed we can work this. Okay. So we can stop for a coffee break.
Yeah, that's
However, the coffee break, I think it is going to take 5 more minutes. And feel free.
Can we stop this thing?